hopefully had a chance to look at the reactions of alkynes. I'll go back here and talk a little bit about how we make alkynes with double elimination reactions. But the bulk of today's stuff was reactions. So did anybody have any questions about those? Okay. We sure about that? Okay, then let me just go back and kind of mop up from last time, since I spent more time on the syllabus than I probably should have. I'm going to spend another minute here on syllabus too. You'll notice that since last semester, the career services didn't have any web page together or any Canvas site for the College of Arts and Sciences Professional Development Program. That I kind of ate the quiz on, or the points for having your resume approved. It's shown up again. So there are 3 things that I'm going to have as assignments. Number 1, getting your resume approved. And if you have a resume approved, then you're good. I would constantly keep it updated. At the beginning of each semester, maybe mid-semester, whenever you have something new and important to put on it, you can always keep your resume up to date. It's always good. Then if somebody wants to offer you a job, you've got the resume right away. Also creating a cover letter, and then creating a LinkedIn page. I mean, I don't always get what LinkedIn is, but students that are out in the real world, like this isn't, say that sometimes when they have jobs, they get recruited for other jobs based on their LinkedIn page. But I know I spent many hours over Christmas break trying to find chemistry alumni back to 2012. And that's only like 6 years ago. But if they had a LinkedIn page, I knew everything. I knew what internships they had, where they were at after they graduated, all of that stuff, and it's really helpful. So if you get like a LinkedIn page now and you become a chemistry major, you're going to help me in the future, because then I'll be able to keep track of where you're at. Not Big Brother-ish, but just because when we're going to have an event where we're going to bring in younger alumni who are working at different places. And so I have no idea how to contact them or where they're at unless I have this huge database of, okay, where are our majors? And so that's why I think now getting into the habit of kind of updating it is a good thing. So those are going to be regular assignments. This semester, though, you may have noticed on Canvas that all of you should have access to a professional development, even if you're not declared. If you don't, send me an email and I'll add you to the undeclared one, to the undeclared Canvas site. So that basically, to do the resume, there's a video you watch, and then there's some handouts, and then you put together your resume, and then you send it over and somebody critiques it, and then you work to get it fixed, and then it goes up on, I guess, Handshake, whatever software they're using. And so there's videos and handouts on how to do this that's now in the website that they told me they would have done last semester, which they failed. So now it's available. I did not go through and check and make sure everybody's name was on that site. If you're already declared as like a bio major, I think you guys have your own. But if you're missing one, let me know, because I'm an instructor for that, so I can put you on it. Okay, so you have the entire semester. I know it'll probably be the last week we'll be trying to do this, but internship season is kind of right around the corner, so having a good resume and a cover letter now will kind of help that, because then there will be another career fair this spring, and so if you have all that together, then you should be in good shape. So that's why I put that assignment in there. And whenever you declare, all of the things you've completed will go with you. So I think in biology, I forget, they have to do, I know in chemistry, people have to do like 5 of the workshops and then an optional 2. And then a career event, which Alicia's working on, putting together with young alumni. And I'll announce that when it's available for anybody. Okay. So that's what's on the syllabus. So that way I don't have to give everybody credit for whether they did it or not, because it's now available. And this is this is, like I said last semester, the university, we're not ahead of the wave in very many things. But this is actually something where we have this program that a lot of schools don't have. And so it's really helpful in terms of trying to get internships and trying to get employment, if everybody's doing this and keeping these things up to date. So there's that in the syllabus. All right, alkynes. So on Monday we said that one of the ways that people usually classify making alkynes is by doing an SN2 reaction on using an alkynyl anion, and the alkynyl anion came from taking a terminal alkyne and treating it with NH2 minus. So that we deprotonate the terminal hydrogen, and then we use the alkynyl anion as a nucleophile. That means that this has to be a primary or secondary halide, and then we end up adding a new alkyl group to the end of the carbon-carbon triple bond. So this is one of the ways to synthesize a triple bond. But as I said, it's kind of cheating, because in order to make the triple bond, you needed a triple bond. So the question is, where did this guy come from? Where did this triple bond come from initially? And so how do you make one of these things from scratch? And the issue there is, okay, if you want to make a triple bond from scratch, we have to think about taking from scratch can mean taking a double bond and making the triple bond from the double bond. And the way we do this is we think about, okay, if I take this double bond and I react it with Br2, what product am I going to get? Right, so now we have to go back to last semester. If you add Br2 to a double bond, what am I adding? For those of you who were with me last semester, 2 Brs. How am I adding them? Markovnikov or anti-Markovnikov? Doesn't matter because it's 2 Brs. Are they adding 100% cis or 100% trans? They go through the triangular intermediate, right? So it's adding trans. So that means, in this case, since there's no ring, the trans isn't necessarily all that important, but I'll write it out as if it kind of looks like it's trans. So I'm adding the 2 Brs, 1 Br per carbon, trans. And so I make this dibromide, which we could call a 1,2 dibromide. The 1 and the 2 mean the relative positioning of them. 1, 2 things mean that the 2 groups are next to each other. This is also sometimes called a vicinal dibromide. And vicinal just means that the groups are next to each other as well.
If we were given 1,2 dibromide, how would we know whether the bromides are cis-trained?
Well, in this case, because there's free rotation, it doesn't matter. And we're going to need the free rotation because now what we're going to do is we're going to do 2 E2 eliminations. And we have to go back and remember, okay, E2 elimination, that means the hydrogen and the bromine have to be anti-periplanar. So in this kind of a system, there's free rotation, we can make that happen. In a ring, this is irrelevant. Because if you think about if I started with a cyclohexane ring, there's no way I can fit a triple bond inside of a 6-membered ring. Because a triple bond has to be linear, and the 6-membered ring isn't big enough to make that triple bond linear. So we only do this on acyclic systems. Okay. But we do have to have the hydrogen and the bromine trans to each other. Okay. So we make the dibromide. And so the next thing we have to do is we have to basically have a base that will come in and grab a hydrogen that is anti-periplanar to the bromine so that it basically kicks off the other bromine. And it doesn't matter in this mechanism if I take a hydrogen on the end or if I deprotonated a hydrogen in the middle. I don't know which one it would do, but it's going to give us then a double bond. So that's the first step, is I'm going to basically now do my first E2 reaction. And so when I do that reaction, what I'm going to end up with is the double bond, and the molecule is going to orient itself so that the hydrogen and the bromine on the double bond have to be trans to each other. In this molecule, I didn't write this hydrogen explicitly anti-periplanar to the bromine, but that's where it would go. Okay. So this E2 reaction means that we still have to be anti-periplanar, the hydrogen in the leaving group. So we do one E2 elimination to form now what would be called a vinyl bromide. A vinyl means that something is attached to the double bond. That's what the vinyl term means. So this is vinyl bromide. If this was a chloride, it would be a vinyl chloride. And if you have something that would be a vinyl chloride, the vinyl chloride is usually reacted to make a long chain polymer. So sometimes you'll hear somebody talk about polyvinyl chloride, which is PVC, which you can make pipes out of. If you see the white plastic pipes, those are PVC. They're made of polyvinyl chloride. The vinyl chloride is the chloride attached to the double bond part. They make albums out of them, or they did, if that's where the vinyl term comes from, right? It's supposedly in now. I don't know that it ever got out of style. Doesn't sound very good. I mean, I still have my 1980s vintage stereo, and it's okay. There's a reason why it disappeared, and probably shouldn't come back, but it is. So when you hear vinyl, that's what it means. Something's attached to double bond. So we made a vinyl bromide. Now I need a second base to come in and grab this hydrogen, have that pair of electrons move there, and kick off the bromine. So I'm using two equivalents of base to do this reaction, and then now what I'm going to do is now I'm going to make then the triple bond. So in this case, that's going to be the final product. So in order to make a triple bond from quote unquote scratch, you need to use a strong enough base that's going to do 2 E2 elimination reactions on a 1,2-dibromo alkane. And the 1,2-dibromo alkane came from the reaction of an alkene with Br2. So that's how we make the triple bond. Now, the only question is, so what base should I use? And the base, in this case, the base that I'm going to use is I'm going to use NH2 minus. That's the base I'm going to use. Because I need a base that's strong enough to do the second step. The base has to be strong enough to do the second step. So, like tertiary butoxide might do the first step, but it won't do the second step. So that's why you'll see, for instance, in the homework problems, I said take the dibromide and react it with 2 NH2 minuses. That means 2 equivalents of NH2 minus. And so you're going to end up then with this alkyne. Does that make sense to everybody? Hopefully, if you went back and watched the video for Wednesday or for Monday, this is what I kind of went over. And this is just one of the 2 possible halides. You could also say, could I, for instance, have the 2 bromines attached to the same carbon and then react this with 2 equivalents of NH2 minus and make the triple bond from this. In order to do this, since I'm going to do 2 E2 reactions, I've got to make sure that if the carbon with the 2 bromines is my alpha carbon, that I've got 2 beta carbons, and so I have to make sure that one of the beta carbons actually has 2 hydrogens. This isn't really a great example because if your next question might be, well, am I going to form the double bond or the triple bond internally, or am I going to form it terminally? And I'll make it fairly simple in terms of saying, okay, I'm going to use a small base. So using a small base means what? It can get to any of the hydrogens equally well. And if I was going to do that equally well, then that means I'm going to form the more stable product. And if I'm going to form the more stable product, which triple bond am I going to make? The internal one or the terminal one? The internal one. So in this particular case, I would make the internal triple bond. So I'm going to, in this case, make the more stable one. And we'll go ahead and we'll leave that as our rule if you have a choice. Now, one of the things we have to be careful of is that if I had an R group on the inside part here, if I had another R group, this carbon does not have 2 hydrogens that could be removed. So that would force it into doing the terminal, to forming the terminal triple bond. So whatever my beta carbon is, it's got to have 2 hydrogens that can be removed. So this is another molecule. This is called, okay, so far we've got, in terms of new terms, we've got vicinal, which means the two groups are next to each other. We've got vinyl, which means that the group's attached to the double bond. This is called a geminal dibromide. And what the geminal term means is that the groups are attached to the same carbon. So there's geminal, there's vicinal, and there's vinyl in terms of those three terms. So this is another way to make a triple bond. Right. Is everybody kind of with me? Now, I'm not a particular, I mean, this works. This is a great method. But how do I make a geminal dibromide? It turns out that to make a geminal dibromide, I need a triple bond to make it. So okay, I already said I had a problem with using a triple bond to make a triple bond. I have the same problem here. I need a triple bond in order to make this molecule to then make the triple bond again. That doesn't seem very efficient. And you're all like, what are you talking about? Here's what I'm talking about. In order to make that molecule, I would need either this triple bond, or I would need the terminal triple bond. My preference would be the terminal triple bond. So how would I make this terminal, what would I add to this terminal triple bond to make this geminal dibromide? Okay, so if I added a Br2, no, I don't need a Br2. I need an HBr. If I add a Br2, why am I wanting to write a Br2? HBr. If I added Br2 to this, I would add two bromines. And what I would add is I would add those two bromines next to each other, trans. What I'd like to do is I'd like to add the bromines to the same carbon. So the first thing I do is add HBr to this alkyne. All right, so when I said on Monday that, triple bonds, we're not going to spend a lot of time on triple bonds because triple bonds they're twice double bonds. I can add two equivalents of things to triple bonds, which means I have to go back and I have to remember what happens with double bonds. So if I add HBr to a triple bond, what am I adding to the triple bond? An H and a Br. How am I adding them? Markovnikov or anti-Markovnikov? Markovnikov. So that means with one equivalent of HBr, I'm going to end up adding the HBr to the triple bond Markovnikovly. Okay. Just for fun. 100% cis, 100% trans, or 50-50? 50-50. Because remember, it goes through a carbocation intermediate. So the HBr would add 50-50. In this case, it doesn't matter because there's no cis-trans possible for this molecule because those two are hydrogens. All right, there's one HBr. If I wanted to turn this molecule into this one, what am I going to add? Another HBr, my second equivalent of HBr. And if I had my second equivalent of HBr, the H is going to add to the end, the Br in the middle. So the way you make a geminal dibromide is by adding two equivalents of HBr primarily to a terminal alkyne. So in order to make this molecule, I need to start with a triple bond. Now, in this whole process, I ended up moving the triple bond from the terminal position to the internal position. So if I want to do that, this is a two-step way of doing that. With this one, what's the problem? If I said I wanted to make this molecule from this internal triple bond, what kind of problem would you anticipate? Hannah. You can ask for help.
Well, you need to add an H and an BR again. I don't know.
Okay. So we need to add an HBr. What's going to happen when I add the HBr to this molecule? Markovnikovly. Carly?
I was going to say it's internal, but can you add something actually comes into the end?
Okay, which one is the end part? If I want to have, Carolyn?
Is it that you can't have the Markovnikovs because each have one hydrogen? So that there's no way of like selecting that?
Actually, each of the two carbons in the triple bond has how many hydrogens? They have 0 hydrogens. So there is no Markovnikov product here. So the H and the Br, I would get a 50-50 split of adding H here, Br here, and vice versa. And then when I go to add the second equivalent of HBr, what happens? I take those two products and I'm going to get 50-50 of those, which means I'm going to end up having like 4 products, and only one of those is going to have 2 bromines in the position that I want it to be. So we would be better off to make this from a terminal alkyne where I do have a Markovnikov product each time, versus this one where I'm going to basically lose 50% of my product because I don't have a Markovnikov product. Does that make sense? So whenever you are adding HBr to this triple bond, you're going to get those 2 products. You're going to add the HBr this way and add the HBr the other way. And then the second equivalent is going to do the same thing to each of those 2 products. So again, you end up with 4 products. So these are the ways that we can make the triple bond from scratch. But using the Geminal Dibromide isn't all that efficient because I needed a triple bond to begin with. Like I said, this is a good example of I want to move the triple bond, do this. But if I just want to form the triple bond to begin with, and it's an internal triple bond, I'm stuck. I'm going to end up losing a ton of product. Jacob?
Going with asymmetrical and come up with Bromide.
Yeah, if it was symmetrical, if both of these were methyl groups, I still am going to have a problem of putting two bromines onto one of the two carbons. In that case, I'd end up throwing away 50% of my product. So I'm still going to have 50% with the two bromines next to each other, and the other 50% with the two bromines on both, or on one of each of the two carbons. And this semester, we're going to pay a little bit more attention to that. Like, we want to make sure that we're making the major product that we want. Okay. You okay with that? Now, this is just the first, doing this reaction of adding 2 HBRs to the triple bond, or adding 1 HBr to the triple bond. That's one of the reactions of alkynes that was in the video for today. So, any questions pop into anybody's mind about the other reactions? Okay, then here's what I will do. Here's 2 reactions of those different reactions that were in the video and in the book. What reagent would I use to add the HBr anti-Markovnikov? What would I use? No Michael here today. Uh-oh. I know this stresses people out, but at least it'll wake you up at 8 o'clock in the morning. Carolyn?
Like HOOH.
And? I'm adding HBr anti-Markovnikov. So I do need the peroxide, and then what am I adding?
HBr.
Yep. So HBr with peroxide, just like last semester, HBr and peroxide adds HBr anti-Markovnikov. So again, if I was looking at this last semester, I would say, what am I adding? HBr. How am I adding it? Anti-Markovnikov. How am I adding it? 50-50 cis-trans. And in this case, I'm going to end up with this product regardless. Actually, no, sorry. I'm going to end up with the bromine both cis and trans to the R group. Now, you could make an argument that which one of those two do you think is more stable? Having the R and the BR cis, or having the R and the BR trans? David?
Trans.
Having the two groups trans? Do we agree with that? Why?
They're both way bigger compared to the hydrogen, so there would be more hindrance.
So if they're cis, there'd be steric hindrance, versus if they're trans, there's not. So I know in the homework problems, somebody asked, do you want us to write the cis or trans or E or Z products? To be honest with you, you can write the more stable one, which would be having the groups trans. In this case, we would get more of that product, but we would actually get them both. So. Okay. So, here's the thing this semester. This semester is a little bit harder than last semester, and by a little bit, people will argue and say it's a whole lot harder, or I guess impossible. Although if it's impossible, then I guess why are we even doing it? But what we have to do is we have to begin to think about what the final product is, but we also have to think about the reagents that I would use to go from A to B. A lot of organic chemists are involved in making molecules, drug discovery, etc. And there's very few complicated drugs that you can make in one step. Sometimes you have to take 26 steps to go from A to whatever. Now in lab, we're going to do, I think, some 5-step reactions. We're going to make benzocaine, which is a sunscreen. And it's going to take us, I think, like 5 steps. So you know how much product you got after the first step, and then take that product and go on to the second step, and then take that product and go on to the third step. I'm out of product, because if each one was like 10% yield, you lost a ton. So when people are doing like a 26-step synthesis, they're always going back and making more of that product. But before you even do that, you have to sit down on paper and think about how to go from A to B to whatever letter of the alphabet you end up with. And in order to do that, we have to kind of think about the reagents. So for the first one, what reagents would you use? Well, you have to look at the reactant in the product and say, okay, what did I add? Did I break a bond? Did I make a new bond? What's different about the molecule? And so in this case, I'd say, I added an HBr, anti-Markovnikov, that's HBr peroxide. But you also have to be able to write the products going forwards as well. So in this case, in the second reaction, what would the final product be? And when we get past today, this might be a reaction where I'd say, okay, go ahead and write this on your phone, or write it, or draw the structure on the computer, or I might give you some structures to choose from A through D. But today, let's just start with the idea of, tell me what the product, describe the product to me.
Adding H and OH.
Okay, I'm adding H and OH how? Markovnikov, anti-Markovnikov. Markovnikov. So that means that the H is going to go at the end and the OH is going to go in the middle. Okay? Cis-trans, 50-50. 50-50, because this would involve a carbocation, right? Okay? So in this case, it doesn't matter, because the molecule I make isn't cis or trans, or E or Z. Okay, am I done? Is that my final product? No. But it makes sense. So what happens is that this molecule is called, what is this molecule called? With the double bond attached, with the OH attached to double bond. This is called an Well, it's an enol that's going to become a ketone. So this is called an enol. Why is it called an enol? Because it's half alkene, half alcohol. And for the most part, enols aren't stable. Maybe towards the end of the semester, we'll talk about some enols that are stable. And if you go on and take like physical chemistry lab, you'll actually do an experiment with NMR that you're going to learn about in lab, where you can actually determine molecules, they have an equilibrium constant between enols and ketones. And it changes as a function of temperature, and it changes as a function of structure. But simple enols that we're going to do in class are unstable. And so they undergo what's called a tautomerization reaction. Okay. So this is an equilibrium reaction, and this is called tautomerization. There's a ton of terminology today. What is tautomerization? It's when you simultaneously move a hydrogen and lone pairs of electrons. These are not resonance structures. These are tautomers. Dr. Weiner and I had to correct a referee on our paper when they said resonance structures, and we're like, no, these are tautomers. Because remember, in resonance structures, you cannot break bonds. So these aren't resonance structures because I'm actually going to move that hydrogen. I'm going to break its bond and form a new one. And that's not resonance structures. So what happens? This pair of electrons comes here to form the CO double bond. So I'm breaking the OH bond. This pair of electrons comes out to bond that hydrogen to the carbon. And so what it ends up doing is we end up forming the double bond to the carbon, and then that hydrogen goes from being bonded to the oxygen to being bonded to the carbon. And so this is a tautomerization equilibrium. And it turns out that for most ketones, or for most of these systems, the ketone is infinitely more stable. It's usually very difficult to isolate simple enols, although it has been done. I think I've seen one paper where they've isolated like the simple enol of acetone, which is a big deal because they're very unstable, but they were able to isolate it. I think the guy that published that paper sent me something when I was a postdoc and said, "Can you get a little crystal out of this so we can figure out what it is?" I was unable to do that, but apparently later on he was. So we always form the ketone. So this is a different kind of reaction. The first step, from what we learned last semester, makes perfect sense. The second step is new. So we form the enol, then the enol undergoes tautomerization. So that's a new reaction. Hydration of an alkyne gives you either a ketone or an aldehyde. And if you wanted to make an aldehyde out of a triple bond, what you would then want to think about is, okay, I'll take my terminal alkyne. I need to add H and OH to it so that I can form so that I can add the H and the OH anti-Markovnikov. So then we have to go back in our memory and remember how did I do anti-Markovnikov addition of H and OH last semester? And we used, Jacob?
BH3 and H2O2.
That's how we did it last semester. And that's called hydroboration oxidation, right? And so what happened was, in this reaction, the boron... Wait, did I write the right product? I did. So when you do hydroboration oxidation, you're adding what? H and OH. How? Anti-Markovnikov. 100% cis, 100% trans. The square. Cis. So actually, remember the boron, the BH2 adds to the carbon that's least sterically hindered. So I'm correct. The H and the OH did add cis. Now, the reason I bring this up is because if I really used BH3 and H2O2, remember how I said on Monday, I believe, that the triple bond is not very sterically, there's not really a lot of steric hindrance because it's a linear system. And if I, okay, so when I do this in the future, when I say, remember, if I didn't say that in this class, then remind me, because what I say in the 1 o'clock class isn't always the same as this one and vice versa. Right? Just like if I say I'm losing it, I'm not really, well, I probably am, but don't be concerned. Got it in my course. In the course evaluations for last year, they're like, I'm afraid for his health because he says he's losing it. It's a phrase. I'm not really, like I said, I'm not really losing it, but I kind of am. So, but don't be concerned with you. But if I say, hey, remember how I said that and I didn't say it, then remind me of that, because then I'll go back and say it. So in one of the two or both classes, I said the triple bond isn't very sterically hindered. So the problem is with a small BH3, I wouldn't get that much discrimination here between adding the H internally and adding the BH3 at the end, because it's small itself. So in the notes, what you'll see is that what we normally do is we add alkyl groups to the boron to make it more sterically hindered, to force it to go to the end of the triple bond, to force it to go to the least sterically hindered end. And there's one where this boron is part of a ring. So that's all I'm doing is I have to touch this reaction. I have to touch it up a little bit because the BH3 is too small. And so we do what we did with turf butoxide, and we basically say, okay, if it's too small and I want to accentuate the sterics, make the reagent more sterically hindered. And then that'll force it to go where I want it to go, which is at the end of the molecule. Okay, so that's the other reaction that isn't quite the same as it was last semester. But a lot of the other ones are. And some of the other ones we'll get to. I can mop up on Friday if you have questions. Like the cleavage. If you remember about cleavage from last semester, we could get aldehydes or we could get carboxylic acids. To cleave a triple bond, I need to use a super harsh oxidizer, and all the super harsh oxidizers will take any aldehyde that you might form and immediately make a carboxylic acid out of it. So we don't have to worry about that for cleavage. We just break the triple bond and put 2 carboxylic acids in place. So cleavage is a little bit different than it was last semester. And ozone, probably not strong enough. Okay. All right. So if you're kind of sitting there today going, oh, I don't remember about my alkene reactions, place to start. And also with the review problems, that's going to help you review and remember a lot of the stuff that we're going to be going over. Including on Friday, there'll be no video. If you want to skim through the book, you could do that or read the book. I'm going to live lecture on Friday, but if you have any questions about any of this, we can start with that on Wednesday. Okay? So the homework problems that I gave you on Monday are due on Wednesday. And if you have questions about any of this stuff, email me or come and see me.